Greetings YouTubers, I'm Rick the Tech Enthusiast here with the next Elegoo lesson number 28, 4-digit 7-segment display. In this lesson we'll check out the Elegoo kit's 4-digit 7-segment display and controlling it with the 74HC595 shift register. We'll build the tutorial sample circuit to demonstrate the functionality, and then we'll build a custom circuit and sketch that provide a better solution to use in our circuits. So let's start building. The 4-digit 7-segment display provided in the kit is a 5641AS common cathode type, which simply means that each digit's LEDs share a common ground, much like the 7-segment display in Lesson 27. There's also a common anode version that shares a common source, but is not included in the kit. Unfortunately, the tutorial's manufacturer's illustration, shown on page 187, is kinda incorrect. The version that is shown has an additional colon and has a wrong part number. However, the remaining information is close enough. It's important to note where pin 1 is located. The digit designation, D1, D2, D3, D4, the digit location, D1 is located on the left and D4 is on the right, and the schematic shown below indicating the pinouts. The datasheet unfortunately isn't even close, but I was able to find one that appears to be correct, or at least closer, and I'll include a copy for you to download. And like in Lesson 27, each digit's LED is assigned a letter that maps to one of the pins in the display. For the 4-digit display, these pins are shared to the other 3 digits. What separates the digits are the 4 common cathode pins. If we control each common cathode's connection, we can turn on a single digit. If we do this fast enough, it will appear that all LEDs are on at the same time. Be sure to check out Lesson 27 to see how the shift register is used to control the 7-segment display. The procedure on the 4-digit display is basically the same, only we'll switch from one digit to the next rather than having them constantly on. The datasheet that I am providing and the tutorial have additional information on the 4-digit 7-segment display, and I encourage you to check them out. For this part of the lesson, we'll need the following items from your kit: the Elegoo UNO R3 board, the 74HC595 shift register IC, the 4-digit 7-segment display, 4 220 ohm resistors, the breadboard, and a bunch of male-to-male jumper wires. On page 188, you'll see the following schematic. And yes, there are a few issues, but I'll bring those up later. The outputs of the shift register are directly connected to the 4-digit display. The DS, the latch clock, and register clock are connected to the Arduino pins 8, 9, and 10. And the 220 ohm resistors will be connected from each D1, D2, D3, and D4 to ground. Okay, let me caution you here. Having all 4 common cathode pins connected to ground, regardless if they're through a resistor or not, will turn on all 4 digits. With this configuration as shown, we really can't control which digit is turned on as we're supposed to. On page 189, you'll see the wiring diagram, with a photo on page 130. Here's where I typically show my version, but I don't want you to use it. I'm embarrassed to say that this circuit and the following sketch is junk. I'll show you why here soon, but first let's jump to the code. As before, we'll load the recommended sketch provided in the tutorial. Go to the File menu item, select Open, and browse to where you saved the Elegoo files. Then under your language, Code, under Lesson 28, 4-digital 7-segment display, 4-digital, and open the 4digital.ino file. Looking at the code, you'll see it starts by defining the various latch, clock, and data pins. which I'll change to match my circuit, which is 11, 9, and 13. This is followed by a char array table. If we look at all the hex values, we can see that at most they are 8 bits long, or 1 byte. A char is 16 bits long. So this array could be defined as a byte rather than char. And of course, my pinout is a little bit different, so I'll add my values here. The void setup sets the pin modes for the latch, clock, and data to output. The void display requires a passed unsigned char parameter num. Now an unsigned char occupies 1 byte of memory. So really, that's the same as saying a byte data type. Anyhow, like the previous lesson, it sets the latch clock low to prevent changes to the shift register output. Then it uses the shift out function to shift out the num value referenced from the table array. Again, check out lesson 27 on how this function works. Then it sets the latch high to enable the shift register output. Next, the void loop then lists a bunch of calls to the display function, followed by a small delay. I also want to point out that though these are valid lines of code, it would have been easier to implement a for loop here and use 2 lines of code to accomplish the same thing. Notice there's nothing in the code to control the individual digits. It's my guess that all the digits will show the same thing at the same time. Let's upload the code and try it out. So you can see here, we have the 4-digit 7-segment display, and all the 4 digits are simultaneously changing from one character to another based on the hexadecimal values that we had in the Arduino code. Unfortunately, we're not controlling any of the digits, and we can't actually do anything separate from each of the code or each of these digits. So I'm not sure how useful this sketch is to anyone. What's important is that the resistors here that are connecting the common cathodes for each of the digits are now connected to ground. What we need to do is we need to control each of these digits common cathodes so that we can control each of the digits independently of each digit. So that way, show one digit value, then switch on another digit and show a value, switch on the third and the fourth. Now you have to remember, this is digit 1, but it's the most significant bit in our list of bits. So you're gonna have to think backwards. This is digit 4, so this is the least significant bit. I'll show you more of that in the next circuit. But otherwise, this circuit is pretty much junk. Here's my circuit. As I indicated in lesson 27, it's better to provide resistors to each LED segment rather than using a common resistor for multiple LEDs. And since each LED can now have 14.5 milliamps of current, 8 LEDs would add up to 116 milliamps, which would easily overpower a single Arduino output pin if we were to use it as a ground source. To overcome the additional current draw and to save the Arduino output pin, we'll need to use a transistor. The kit includes 5 PN2222 type NPN transistors. We'll need 4. Transistors have 3 connections: a collector, a base, and an emitter. Transistors are typically used for amplification, rectification, and switching. We'll use it for switching. The datasheet lists the PN2222 maximum current rating as 600 milliamps, I'll bet using a heatsink, so we'll be well under that amount. We'll use an output from the Arduino to turn on or off the transistor, thus using the transistor to connect a single digit's common cathode to ground. I laid out the circuit to be easier to follow. The shift register is on the right, so to its left is 8 220 ohm resistors, then the 4-digit display, and then the transistor controls. The output of the shift register is connected to one of the 8 resistors. Q0 jumps down and then back up through the resistor and then to the 4-digit display pin 11. Q1 goes left to a resistor and up to pin 10. Q2 goes across to the resistor and up to pin 7. Now outputs Q3 through Q7, I had to use longer jumpers. They swing over to one of the jumpers that span the gap in the breadboard that leads up to a small jumper to connect to the next column of pin connections and down to a resistor that spans the gap of the breadboard to meet up with another long jumper that swings over to the 4-digit display. Here's a diagram showing the 4-digit display pinouts. Pins start from the bottom left and work around counterclockwise to pin 12. Pins 1 through 5 control the LED segments E, D, the decimal point, C, and G. Pin 6 is for the D4 pin, which controls the right or least significant digit. Pin 7 controls the LED segment B. Pins 8 and 9 control D3 and D2. Pins 10 and 11 control LED segments F and A. And lastly, pin 12 controls D1, which is the left or the most significant digit. Pins D1 through D4 are connected to one of the transistor's collectors. The transistor's emitters are all connected to ground. Their bases are connected to the Arduino pins 4 through 7 through 5 kilo ohm resistors. Note that the Arduino's output needs to go high to switch on the associated transistor. Here's the schematic. It may be clear to see how the 220 ohm resistors are connected between the shift register and the 4-digit display, and how the Arduino pins 4 through 7 will activate the transistors to turn on or off each digit. The rest is coding, so let's check out the sketch. The sketch begins with constants to define the data pin, the latch pin, the clock pin, and what I call digit 0 through digit 3. I'll use digit 0 as the least significant bit and digit 3 as the most significant bit, but more on that later. I revised the table array as a byte data type with the hexadecimal values provided by this table. Like in lesson 27, I have the desired output on the left column and the output pin ordered from 7 through 1 on top. And below that, I have the associated LED segments connected to those output pins. How did I determine the pin order? Really, it doesn't matter. If you start with pin 7 as the least significant bit, I'll need to use the LSB first in my sketch. But I have pin 7 as the most significant bit, so I'll use MSB first in my sketch. Simple. As before, I manually add a 1 for every LED segment I want on for the corresponding output. For example, if we look at 0, we see segments A, B, C, D, E, and F should be enabled. So I add a 1 in the row 0 under columns A, B, C, D, E, and F. The spreadsheet calculates the decimal values for me and then converts those values to hexadecimal and binary. Now all I need to do is copy these values to my code. Byte digit DP is used to hold the decimal point segment value. I'm showing it as a decimal, but it could have been a hexadecimal or binary. If the decimal point was needed, simply add the digit DP to the byte where you call out the shift out command. Unfortunately, I didn't really incorporate this feature in the code, perhaps a future video. Well, anyhow, this is followed by two byte arrays, control digits and display digits. Control digits store the Arduino pins that I will use to control each of the 4 digits. By putting them in an array, it'll make coding that much easier. And with that same logic, display digits will hold the actual digit values starting with the least significant bit and up to the most significant bit. The 5th element, or the 4th index item, will hold the digit switch. The least 4 bits of the digit switch will tell the sketch how to treat the previous display digit values. If the associated bit is a 0, the code will check the table array. If it is 1, assume that is a raw bit value. More on that later. There's an unsigned long on time to track the time, a boolean to switch between 2 different views, which I'll discuss later, and an unsigned int counter. Global adjust variables. These global values can be adjusted as needed. There's a digit delay, brightness, and show segment count. The first 2 are kind of self-explanatory. The show segment count is a crude way to control the length of time the raw display view remains on. Void setup sets the pin modes for the latch, clock, and data pins to output. The for loop is used to set the digit 0 through digit 4 pins to output. Having each of these inside the control digits array makes it easy to handle them with a loop. Void display segments replaces what was the display function. This time I've chosen not to add a parameter since the values to be displayed are in the global display digits array. It starts with a for loop, which will loop through the values of x from 0 to 3. The second for loop does this as well, except it uses j, and it simply performs a digital write to each control digit to set them to low. The low value turns off the transistor and thus turns off all the digits. Like in the previous display function, the next line of code sets the latch pin to low, disabling changes in the shift register output. The next if statement performs a bit read in the digit switch stored in the display digits array, and it's always index 4, at position x, and checks if that bit equals 1. If true, shift out the raw bit value. If not, shift out the value from the table array using the index stored. Neat, huh? The next digital write sets the latch pin high, allowing the output to change to new values. Then the corresponding control digit is set to high, which turns on the single digit. So for example, we'll start with the first for loop and the x value as 0. This if statement will read the 0 bit from the digit switch stored in the display digits array. If the 0 bit is 1, shift out the raw byte value stored in the display digit 0. Else, shift out the table array value using the display digits value as an index. Next, the latch is set high and the control digit 0 is turned on. See? Simple. This is followed by a very small delay, and it repeats for the remaining digits. The last for loop turns off any remaining digits. Void hex counter function is used to count in hexadecimal from 0 to FFF. I originally had a 4-digit counter, but it took a very long time to increment through all those numbers, so I changed it to 3 digits. But I've added a raw data value for the most significant digit, making this display sort of a mix mode. It starts with a local byte, letter, assigned to some binary value, which happens to be letter C. Another local variable, increment value, is a boolean and is set to true. This is used to keep track of the digits that need to be incremented. Each time the function is called, the least significant bit needs to be incremented. The for statement loops through each digit to check to see if they need to be incremented. First, it gets the digits stored in the display digits array at the appropriate location and sets the integer variable x to that value. If incremented value is true, increment x and set the increment value to false. Now, if the new x value is greater than 15, reset the display digit value at that current location to 0 and set the increment value to true. This way, the next digit will also be incremented. Else, set the display digit at the current location to the new value of x. This is repeated for the next two digits. Notice that for the first if statement, if the increment value is false, it skips the remaining lines of code. Next, the display digit 3 is set to the variable letter. Remember, this is actually the fourth item in the array because arrays start with 0. Then the display digit 4 is set to binary 1000. Since the fourth digit is to be handled as a raw value, the bit representing that digit needs to be set to 1, while the others are set to 0. The last if statement checks if the counter is finished. If true, switch the view. Reset the display digits and the display digit index 4, which is the digit switch, to 0. The void raw display function demonstrates assigning each digit a raw binary value to be displayed. Display digits index 4, the digit switch, is set to be binary 1111 since all the display digit values are to be treated as raw values. The if statement increments the counter if it's less than the show segment count. If not, reset everything and change the switch view. Finally, the void loop, which is the simplest, and it needs to be. In order to fool the eyes into thinking that all 4 digits are on, the void loop needs to loop quickly and avoid any unnecessary delays. The first thing it does is call the display segment function, which displays each digit for 1 millisecond. The next line will control the brightness. By adding a delay in microseconds, we effectively dim the digits. 16,383 is the largest value delay microseconds can use, which is a little over 16 milliseconds. Values greater than this can start to cause the LED to flicker. Next, the now value, which is an unsigned long, is set to the millis minus the last on-time value. This will determine if enough time has passed to exceed the digital delay value. If it is, on time is set to the current millis, which gets the current time. Then it shows either the raw display or the hex counter. And that's it. It rapidly loops through the display segments until the next digit delay is met. Let's upload the code and check it out. All right, so here's the circuit. As you can see on the right-hand side, we have the shift register, and then we have the 8 220 ohm resistors. We have the 4-digit display, and the 4 transistors that will be used to control the common cathodes of each of the digits. Now, like I explained before, this is digit 4, which I'll use as digit 0, the least significant bit. And this is digit 1, which I'll use as digit 3, the most significant bit. Here's a hexadecimal counter. It's now counting up from 000 to FFF. The C is the raw data value that I sent to display. And the brightness, I believe, is at around 90. 90, is it right? I forget what I set that to. You can see I kept the pin modes or pins the same for the data, latch, and clock like I had in my previous sketches or lessons, but the shift register had to be scooted over to make room for all the additional components. Here we have the 3 connections to the transistor here. We have the emitters that are going to ground. You can see that each one of these are going to ground. And the collectors, we have this one coming from D4, and the D3 and D2 and D1 are coming from above, going through the little jumpers right here, and then connecting to the collectors on the transistors. The base is then controlled by each of the Arduino pins here. What is important to note is even though this is a large breadboard, it's not the one that comes with the Elegoo kit. I had a separate breadboard. I do perform this all in a single breadboard, and unfortunately this convention has the breadboard with the positive rail on the bottom and the negative rail on the top, where I typically have it reversed because I just like it that way. Just a preference. It's not an absolute requirement. But just be careful when you're doing your circuit that you, whichever way you have your rails, you correct or use the right pins to the right positive and ground rails that you have in your circuit. You can see now it's counting. I'm trying to see what we have here. We're getting close here. Like I said before, this was a 4-digit counter, and this took a long time, even as with a little delay that I currently have to get to the raw value display and then switch back to the counter again. So I switched it to a 3-digit counter just to speed things up. Here we're almost to the end. A, B, C, D, E, F, and there we go. So halo is the raw digit display. It'll do this, I believe, for 250 counts, and then it begins to count up again. And that's it. You can see that the brightness is even for all the LEDs, no matter how many LEDs for a digit is showing. That's the benefit of having devoted resistors to each LED segment. Well, that's it for this lesson. I hope you've enjoyed learning a little about the 4-digit 7-segment display. If you like this sketch, be sure to let me know in the comments section below. I'll have additional links for other interesting videos and code for this project in the show notes below. Join me next time for lesson 29, DC motors. And if you like this video, give it a big thumbs up, subscribe, and click the notification bell to get notified when I upload new videos. Thanks, and see you next time.